Hello and welcome to Earth Science, Lecture 33, The Jovian Planets and Small Solar System Bodies. The four Jovian planets, in order from the Sun, are Jupiter, Saturn, Uranus, and Neptune. Because of their location within the solar system and their size and composition, they are also commonly referred to as the outer planets or the gas giants. The giant among planets, Jupiter, has a mass 2.5 times greater than the combined mass of all other planets, satellites, and asteroids in the solar system. Jupiter orbits the Sun once every 12 Earth years, but it rotates more rapidly than any other planet, completing one rotation in slightly less than 10 hours. When viewed telescopically, the effect is noticeable because of its fast spin. The bulge of the equatorial region and the slight flattening at the poles are evident. Jupiter's appearance is mainly attributable to the colors of light reflected from the three main cloud layers. The warmest and lowest layer is composed mainly of water ice and appears bluish-gray, while the middle layer, where temperatures are lower, consists of a brown to orangish-brown cloud of ammonium hydrosulfide droplets. These colors are thought to be a byproduct of chemical reactions occurring in Jupiter's atmosphere. Near the top of its atmosphere lie the white wispy clouds of ammonium ice. Because of its immense gravity, Jupiter is actually shrinking a few centimeters every year. This contraction generates most of the heat that drives Jupiter's atmospheric circulations. Thus, unlike winds on Earth, which are driven by solar energy, the heat emanating from Jupiter's interior is producing the huge convection currents observed in its atmosphere. Jupiter's convective flow produces alternating dark-colored belts and light-colored zones. The light clouds, or zones, are regions where warm material is ascending and cooling, whereas the dark belts represent cool material that is sinking and warming. This convective circulation, along with Jupiter's rapid rotation, generate the high-speed, east-to-west flow observed between the belts and zones. The largest storm on the planet is the Great Red Spot. This enormous anticyclonic storm, twice the size of Earth, has been known for 300 years. In addition to the Great Red Spot, there are various white and brown oval-shaped storms as well. The white ovals are the cold cloud tops of huge storms many times larger than hurricanes on Earth. The brown storm clouds reside at lower levels in the atmosphere. Lightning in the white oval storms have been photographed by the Cassini spacecraft, but the strikes appear to be less frequent than on Earth. Jupiter's magnetic field, which happens to be the strongest in the solar system, is probably generated by a rapidly rotating liquid metallic hydrogen layer that surrounds its core. Bright auras associated with the magnetic field have also been photographed over Jupiter's poles. Unlike Earth's auroras, which occur only in conjunction with heightened solar activity, Jupiter's are continuous. Jupiter's satellite system consists of 67 moons discovered thus far, and resembles a miniature solar system. Galileo actually discovered 4 of the largest satellites, which we call Galilean satellites, in 1610. The 2 largest, Ganymede and Callisto, are roughly the size of Mercury, whereas the 2 smaller ones, Europa and Io, are about the size of Earth's moon. The 8 largest moons appear to have formed around Jupiter as the solar system condensed. Jupiter also has very many small satellites, most of which revolve in the opposite direction, in other words, in retrograde motion, of the larger moons, and have eccentric or elongated orbits that are steeply inclined to the Jovian equator. These satellites appear to be asteroids or comets that had passed near enough to either be gravitationally captured by Jupiter or are remnants of the collisions of larger bodies. The Galilean moons can be observed with binoculars or on a small telescope and are interesting in their own right. Images from Voyagers 1 and 2 revealed, to the surprise of most geoscientists, that each of the 4 Galilean satellites are completely unique worlds. The Galileo mission also unexpectedly revealed that the compositions of each satellite is strikingly different, implying a different evolution for each. For example, Ganymede has a dynamic core that generates a strong magnetic field not observed in other satellites. The innermost Galilean moon, Io, is perhaps the most volcanically active body in our solar system. More than 80 active sulfurous volcanic centers have been discovered. Umbrella-shaped plumes have been observed rising from Io's surface to heights exceeding 60 miles. The heat source for volcanic activity happens to be tidal energy generated by a relentless tug-of-war between Jupiter and the other Galilean satellites, with Io as the rope. The gravitational field of Jupiter and the other nearby satellites pull and push on Io's tidal bulge as its slightly eccentric orbit takes it alternately closer and farther from Jupiter. This gravitational flexing of Io is transformed into heat, similar to the back and forth bending of a piece of sheet metal, and resulting in Io's spectacular sulfurous volcanic eruptions. Lava, thought to be mainly composed of silicate minerals, regularly erupts on its surface. One of the best prospects of finding liquid water within our solar system lies beneath the icy surface of some of Jupiter's moons. For example, detailed images from Galileo have revealed that Europa's icy surface is quite young and exhibits cracks apparently filled with dark fluid from below. This suggests that under its icy shell, Europa must have a warm, mobile interior, perhaps an ocean. Because liquid water is a necessity for life as we know it, there is considerable interest in sending an orbiter to Europa, and eventually a lander capable of launching a robotic submarine to determine whether it harbors life. Requiring more than 29 Earth years to complete one revolution, Saturn is almost twice as far from the Sun as Jupiter. Yet their atmospheres, compositions, and internal structures are actually remarkably similar. The most striking feature of Saturn is its ring system, first observed by Galileo in 1610. Through his primitive telescope, the rings appear as 2 small bodies adjacent to the planet. Their ring nature was determined 50 years later by Dutch astronomer Christian Huygens. Saturn's atmosphere, like Jupiter's, is dynamic. Although the bands of clouds are fainter and wider near the equator, rotating storms similar to Jupiter's red spot occur in Saturn's atmosphere, as does intense lightning. Although the atmosphere is 93% hydrogen and 3% helium by volume, the clouds, or condensed gases, are composed mainly of ammonium, hydrosulfide, ammonia, and water, each segregated by temperature. Also, much like Jupiter, Saturn emits roughly twice as much energy as it receives from the Sun. This implies that it must have an internal heat source, which may come from chemical differentiation in its interior. In the early 1980s, the nuclear-powered Voyagers 1 and 2 explored Saturn to within 100,000 miles of its cloud tops. More information was collected about Saturn in that short time than had been acquired since Galileo first viewed these elegant planets in the 1600s. More recently, observations from ground-based telescopes, the Hubble telescope, and the Cassini-Huygens spacecraft have added to our knowledge of Saturn's ring system. In 1995 and 1996, when the positions of Earth and Saturn allowed the rings to be viewed edge-on, Saturn's faintest rings and satellites became visible. These were visible again and viewed edge-on in 2009. Saturn's ring system is more like a large rotating disk of varying density and brightness than a series of independent ringlets. Each ring is composed of individual particles, mainly water ice with lesser amounts of rocky debris, that circle the planet with regularly impacting one another. There are only few gaps most of the areas that look like empty space contain either fine dust particles or coated ice particles that are efficient light reflectors. Most of Saturn's rings fall into two categories based on density. Saturn's main and bright rings, designated A and B, are tightly packed and contain particles ranging in size from a few centimeters, or pebble-sized, to tens of meters, or house-sized, with most of the particles being roughly the size of a large snowball. In these dense rings, particles collide frequently as they orbit the planet. Although Saturn's main rings, A and B, are 25,000 miles wide, they are actually very thin, only 30 to 100 feet from top to bottom. At the other extreme are Saturn's faint rings. Saturn's outermost ring, the E ring, is composed of widely dispersed tiny particles. Recall that cryovolcanism, that is the eruption of water ice mixture, on Saturn's satellite Enceladus is thought to be the source of material for this E ring. Studies have shown that the gravitational tugs of nearby moons tend to shepherd the ring particles by gravitationally altering their orbits. For example, the F ring, which is very narrow, appears to be the work of satellites located on either side that confine the ring to being that confine the ring by pulling back particles that try to escape. On the other hand, the Cassini division, a clearly visible gap, arises from the gravitational pull of Mimas, one of Saturn's moons. And let's see, you can see the ring labels clearly labeled here, just for clarity. And there's the Cassini division. So some of the ring particles are believed to be debris ejected from the moons embedded in the rings. It is also possible that material is continually recycled between the rings and the ring moons. The ring moons gradually sweep up particles, which are subsequently ejected by collisions with larger chunks of ring material, or perhaps by energetic collisions with other moons. It seems then that planetary rings are not the timeless feature that we once thought. Rather, they are continuously recycled. The origin of planetary ring systems is still being debated. Saturn's rings probably formed when objects like comets, asteroids, or perhaps even moons were pulled apart by Saturn's strong gravity. Pieces of these objects would have collided with each other, breaking into even smaller pieces. Collisions among these fragments would tend to jostle one another and cause them to spread out to form the flat, thin ring system that we observe today. Saturn's rings, as well as those of the other planets, are thought to be short-lived compared to the age of our solar system. This means that Saturn probably lacked rings early in its history, and its existing ring system will likely dissipate in the distant future. The Saturnian satellite system consists of 62 known moons, of which 53 have been named. The moons vary significantly in size, shape, age, and origin. Some of the moons are original satellites that formed in tandem with the parent planet. But most of Saturn's smallest moons have irregular shapes and are only a few tens of kilometers in diameter. Saturn's largest moon, Titan, is larger than Mercury and is the second largest satellite in the solar system. Titan and Neptune's Triton are the only satellites in the solar system known to have substantial atmospheres. Titan was visited and photographed by the Cassini-Huygens probe in 2005. The atmospheric pressure at Titan's surface is about 1.5 times that at Earth's surface, and the atmospheric composition is about 98% nitrogen and 2% methane, with trace amounts of organic compounds. Titan has Earth-like landforms and geological processes, such as dune formation and stream-like erosion, but it's caused by methane rain, not liquid water rain. In addition, the northern latitudes appear to have lakes of liquid methane. Enceladus is another unique satellite of Saturn, one of a few icy moons that erupt fluid ice containing minor amounts of other debris. This amazing manifestation of volcanism, known as cryovolcanism, from the Greek word cryos, meaning frost, describes the eruption of magmas derived from the partial melting of ice instead of actual rocks. In the southern polar regions, areas called tiger stripes, consisting of large fractures with ridges on either side, erupt geyser-like plumes. The material ejected by these eruptions is thought to be the source of material that replenishes Saturn's E-ring. Although Earth and Venus have many similar traits, Uranus and Neptune are perhaps more deserving of being called twins. They are nearly equal in diameter, both about 4 times the size of Earth, and they are both bluish in appearance, as a result of methane in their atmospheres. Their days are nearly the same length, and their cores are made of rocky silicates and iron, similar to the other Jovian planets. Their mantles, made mainly of water, ammonia, and methane, are thought to be very different than those of Jupiter and Saturn. One of the most pronounced differences between Uranus and Neptune, however, is the time that they take to complete one orbit or revolution around the Sun, 84 versus 165 Earth years respectively. Unique to Uranus is the orientation of its axis of orbit, the axis of rotation. Whereas the other planets resemble spinning tops as they circle the Sun, Uranus is like a top that has been knocked on its side, but remains spinning. This unusual characteristic of Uranus is likely due to one or more impacts that essentially knocked the planet sideways from its original orientation early in its evolution. So Uranus actually rotates at about 90 degrees on its side. Uranus shows evidence of huge storm systems larger than Earth's continents. Recent photographs from the Hubble Space Telescope also reveal banded clouds composed mainly of ammonia and methane ice, similar to the cloud systems on the other Jovian worlds. Spectacular views from Voyager 2 showed that Uranus's 5 largest moons have varied terrains. Some have long, deep canyons and linear scars, whereas others possess large, smooth areas on otherwise crater-riddled surfaces. Studies conducted at NASA's Jet Propulsion Laboratory suggest that Miranda, the innermost of the 5 largest moons, was recently geologically active, most likely driven by gravitational heating as occurred on Io, discussed earlier. A surprise discovery in 1977 showed that Uranus actually has a ring system. The discovery was made as Uranus passed in front of a distant star and blocked its view, a process called occultation. Observers saw the star wink, quote-unquote, briefly 5 times, meaning that there were 5 rings, before the primary occultation and, again, 5 times afterward. More recent ground and space-based observations indicate that Uranus has at least 10 sharp-edged, distinct rings orbiting its equatorial region. Interspersed among these distinct structures are broad sheets of dust. Because of Neptune's great distance from Earth, astronomers knew very little about this planet until 1989. 12 years and nearly 3 billion miles of Voyager 2 travel provided investigators an amazing opportunity to view the outermost planet. Neptune has a dynamic atmosphere, much like that of the other Jovian planets. Record wind speeds approaching 1,500 miles per hour encircle the planet, making Neptune the windiest place in the solar system. Neptune also exhibits large dark spots, thought to be rotating storms similar to Jupiter's Great Red Spot. However, Neptune's storms appear to have comparatively short lifespans, usually only a few years. Another feature that Neptune has in common with Uranus is its layers of white cirrus-like clouds, probably frozen methane, about 30 miles above the main cloud deck. Neptune has 14 known satellites or moons, the largest of which is Triton. The remaining 13 are small, irregularly shaped bodies. Like Enceladus, Triton exhibits cryovolcanism. Triton's icy magma is a mixture of water ice, methane, and probably ammonia. When partially melted, this mixture behaves as molten rock does on Earth. In fact, upon reaching the surface, These magmas can generate quiet outpourings of ice lavas that can flow great distances from their source, similar to fluid basaltic lava flows here on Earth. They also occasionally produce explosive eruptions that can generate the ice equivalent of volcanic ash. In 1989, Voyager 2 detected active plumes on Triton that rose 5 miles above the surface and were blown downwind for more than 60 miles. Neptune has 5 named rings. 2 of them are broad, and 3 are narrow, perhaps no more than 60 miles wide. The outermost ring appears to be partially confined by the satellites Galenta. Neptune's rings, like Jupiter's, appear faint, which suggests that they are composed mostly of dust-sized particles. Neptune's rings also display red color, indicating that dust is composed of organic compounds. So that is the last actual planet in our discussion. So now we can step out into some of the smaller bodies of our solar system. Asteroids are small bodies, or planetesimals, that remain from the formation of the solar system, which means that they are about 4.6 billion years old. The orbits of more than 100,000 asteroids has been accurately measured, and thousands more have orbits that are incompletely known, keeping them off the official list. Most asteroids orbit the Sun between Mars and Jupiter in a region known as the asteroid belt. There are only about 24 asteroids that are more than 125 miles across. However, our solar system hosts an estimated 1 to 2 million asteroids larger than 0.6 miles across, and many millions more that are smaller. A smaller number of asteroids travel along eccentric orbits that take them near the Sun, and about 1,300 of these, called Earth-crossing asteroids, will eventually collide with Earth. Many of the recent large impact craters discovered on Earth resulted from collisions with asteroids. Although these events are rare, they merit our attention because of their potential destruction. As a result, observational initiatives that aim to measure asteroid orbits with great accuracy are ongoing. The asteroid in this image, 433 Eros, is only 21 miles long and 8 miles wide, about the same size as the island of Manhattan. Because Eros is so small, its gravity is actually too weak to have pulled it into a spherical shape. One common misconception about asteroids is that they are the remnants of an ancient planet that somehow broke apart or exploded, like the fictional planet Krypton in the comic book Adventures of Superman. In fact, the combined mass of all the asteroids is much less than the mass of the Moon, and they were probably never any part of a planet-sized body. The early solar system is thought to have been filled with asteroid-like objects, most of which were incorporated into the planets. But the leftover objects that missed out on this make up the present-day populations of our asteroids. The outer solar system hosts what we know as trans-Neptunian objects. These are small bodies whose orbits lie beyond the orbit of Neptune, our furthest planet. Most comets originate in one of 2 regions, either this Kuiper belt or the OORT cloud, which we'll talk about next. Named in honor of astronomer Gerald Kuiper, who predicted its existence, the Kuiper belt hosts a large group of icy objects that reside in the outer solar system, again beyond the orbit of Neptune, from about 30 to 50 AU, or astronomical units. Pluto's orbit lies within this Kuiper belt, and in 2005, scientists discovered Eris, a Kuiper belt body more massive than Pluto. Like most bodies located in the inner solar system, Kuiper belt comets orbit the Sun in the same direction and along roughly the same plane as the planets. This disc-shaped structure is thought to contain about 100,000 bodies more than 60 miles across, as well as many smaller objects too. The combined mass of all trans-Neptunian objects is comparable to the mass of Jupiter, and is several hundred times greater than the combined mass of all the asteroids that we find in the inner solar system. Like asteroids, trans-Neptunian objects are thought to be debris left over from the formation of the solar system. In the inner regions of the solar system, rocky fragments have been able to endure continuous exposure to the sun's heat. But any ice originally present would have evaporated. Far from the sun, ice has survived for billions of years. Thus, debris in the solar system naturally divides into two families: the rocky asteroids and partially icy trans-Neptunian objects, which can be arranged according to distance from the sun, just like the two categories of planets, terrestrial and Jovian. So this brings us then, of course, to Pluto. Discovered in 1930 was Pluto, with a diameter of only 2,274 kilometers. This is larger than any asteroid, but it's also far smaller than any planet or any of the moons listed in any common tables of moons. The orbit of Pluto has a greater semi-major axis, or distance from the sun, of almost 40 astronomical units. It is more steeply inclined at 17 plus degrees, so it doesn't lie necessarily in the same plane as the other planets, and has a greater eccentricity of 0.25 than any of the other planets. In fact, Pluto's non-circular orbit sometimes takes it nearer to the sun than Neptune. Pluto's density is also kind of in the middle, at 2,000 kilograms per meter cubed, less dense than the terrestrial planets, but more dense than the Jovian ones. Hence, its composition is thought to be a mixture of about 70% rock and 30% ice. So, this was discovered again in 1930 by Clyde Tombaugh, who was searching for a yet undiscovered planet in order to explain irregularities in the orbit of Uranus. Astronomers quickly realized that Pluto was too tiny and too distant to account for such irregularities. Pluto has a diameter of just 1,470 miles, or 1/5 that of Earth, and less than half that of Mercury. More attention was given to Pluto's status as a planet when astronomers began to discover other large Kuiper belt bodies. Clearly, Pluto and these other large Kuiper belt bodies were completely different from either the terrestrial or Jovian planets. So, in 2006, the International Astronomical Union, the group responsible for naming and classifying celestial objects, voted to designate a new class of solar system object called dwarf planets. To be classified as a dwarf planet, a celestial body must orbit the sun and be essentially spherical due to its own gravity, but not large enough to sweep its orbit clear of other debris. By this definition, Pluto is recognized as a dwarf planet, and the prototype for this new category of planetary objects. In July of 2015, NASA's New Horizons spacecraft shot past Pluto after a 9-year journey that brought it within 7,800 miles of Pluto's surface. Images transmitted from the New Horizons show Pluto to be an active body with several distinct terrains, including mountainous areas consisting of blocks of water ice, flat ice plains composed of nitrogen ice, and rugged areas indicating a long history of impacts. And then we go to the farthest possible distance in our solar system. Comets, like asteroids, are also leftover material from the formation of the solar system. They are loose collections of rocky material, dust, water ice, and frozen gases such as ammonia, methane, and carbon dioxide. Thus, the nickname dirty snowballs is often used for them. Recent space missions to comets have shown their surfaces to be dry and dusty, which indicates that their ices are hidden beneath a layer of rocky debris. Most comets reside in the outer reaches of the solar system and take hundreds of thousands of years to complete a single orbit around the sun. However, a smaller number of short-period comets, those having a period of less than 200 years, such as the famous Halley's Comet, make regular encounters with the inner solar system. The phenomena associated with comets comes from a small central body called the nucleus. These structures are typically 1 to 10 kilometers in diameter, but comet nuclei 40 kilometers across have been observed. When a comet comes within 5 astronomical units of the sun, solar energy heats the surface sufficiently to cause its icy components to begin to vaporize into a gas. The escaping gases carry this dust from the center of the comet's surface producing a huge dusty atmosphere called a coma. As a comet approaches the inner solar system, the coma grows, and some of the dust and gas is pushed away from the sun to form the comet's tail, which can grow to hundreds of millions of kilometers in length. Bright comets have two visible tails, a dark blue tail that points directly away from the sun, and a brighter tail that points away from the sun, but also curves slightly in the direction that the comet came from. Scientists have determined the mechanism that accounts for the formation of these tails. The faint, straight gas tail consists of ionized cometary gas that are pushed away from the coma by the pressure of the solar wind, of charged particles emitted from the sun. The brighter, curved dust tail consists of dust particles that are pushed away from the coma by the much weaker pressure of sunlight, or radiation pressure. The dust tail is curved because it's bright. Relatively slow-moving particles record how the direction toward the sun changes as the comet moves along its orbit. As the comet's orbit carries it away from the sun, the gases forming the coma dissipate, the tail disappears, and the comet returns to its cold storage. Material that was blown away from the comet to form the tail is now lost forever. When all these gases are expelled, the inactive comet continues to orbit without a coma or tail. Sometimes the comet literally disintegrates into smaller fragments that continue to orbit the sun. Scientists believe that few comets remain active for more than a few hundred close orbits of the sun. In 2015, the Rosetta spacecraft, launched by the European Space Agency, obtained a close-up image of the nucleus of comet 67P, which you see in the top right, that offered a new perspective on the extent of a comet's activity. The figure shows jets of gas and dust emanating from the central region of the nucleus and extending toward the upper right of the image. This image also shows the nebulous glow of material escaping the bright, sunlit surface of the comet. So where do we find these comets? Well, named for Dutch astronomer John Oort, the Oort cloud consists of icy planetesimals that form a roughly spherical shell around the entire solar system. Oort cloud objects have random orbits, forming a spherical halo at distances often greater than, get this, 50,000 AUs. In other words, 50,000 times further away from the sun than the Earth. This places them nearly half the distance to Proxima Centauri, the next closest star. These icy objects are so loosely bound to the solar system that the gravitational effects of a distant passing star may send an occasional Oort cloud body, or comet, into highly eccentric orbits that carry it toward the sun. Because most comets that encounter the inner solar system have random orbits, these are assumed to have come from the Oort cloud. The Oort cloud is estimated to contain at least 1 trillion comets. How did so many comets end up in the outer reaches of the solar system? Well, the most widely accepted hypothesis is that these bodies formed early in the solar system's history in the region occupied by the still developing Jovian planets. Rather than being captured by one of these growing planets, the comets were gravitationally flung outward in all directions. And with that, we will conclude our tour of the solar system. So now, let's do a bunch of questions relating to these last 2 lectures on the planets. Question number 1. What is the origin of the layer of debris called lunar regolith on the surface of the moon? Okay, so that really grainy, kind of dust-like or soil-like surface is caused by repeated impacts of meteors, and it happens to be anywhere from 6 to 66 feet thick. Question 2. Which body is shown in this image? Okay, in this case, we are looking at Mercury. Usually, I get a response of either Mercury or the moon because they look so similar. In this case, it is Mercury. Notice that it lacks those darker maria like we talked about on the moon. Question 3. What rotates in the opposite direction of the other planets? Okay, so in this case, it is Venus. Venus rotates in the opposite direction of the other planets, and it has a day that's 243 days long. Question 4. The solar system's largest known volcano is found on which planet? Okay, in this case, the answer is Mars. Olympus Mons is the solar system's largest known volcano. Question 5. What has an axis of rotation that is sideways compared to the other planets? In this case, the answer is Uranus. We believe that this is due to an impact that knocked it on its side. Which planet is shown here? Okay, so it's one of the two blue gas giants. You could probably narrow it down to two, I hope. In this case, it is Neptune. Neptune exhibits large dark spots, thought to be rotating storms similar to Jupiter's Great Red Spot. And last but not least, question number 7. Where is the asteroid belt located? Okay, so hopefully your response is between Mars and Jupiter. Basically between our terrestrial and Jovian planets. All right, so with this, we actually conclude our solar system discussions. We then will, next week or in the next couple lectures, jump to our final topics of this course: the sun, the stars, and perhaps, if we have time, the universe. Thanks for watching, and have a great day.